Hello everyone. Today I'm going to walk through setting up a sim like the one we see here, doing that inside of Houdini. In making this, I used all standard nodes, used the standard flip solver with a few tweaked parameters and a couple of other just standard dot nodes. I'm also going to show you a way to build velocity fields from curves, giving you more control over the look and the shape of your splashes. There's a lot of information to cover with this setup, so let's hop inside and get going. So the first thing I want to go over is how to build a tool for controlling the shape and the direction of this splash. As with most things in Houdini, there's a lot of ways to do it, and there's not really a wrong way. It's whatever way you feel like fits your needs the best. So I chose this way because I feel like using curves, and you're going to see here I have a geometry node called velocity fields, and I'm going to build some curves inside here. I feel like having the ability to look at a curve and say, my particle is going to start down here and it's going to travel up this curve, that's exactly what I want. And then it also gives me some flexibility to just manipulate those points manually, as well as using noise to give some definition and shape to those curves. So let me start the process of explaining how this is going to work with a single, just a single line. So I'm actually going to drop down a line, stop. I'm going to resample it. All right. And now, so actually, while I'm in here, I'm going to just give this a little bit of a shape. I just did that with a soft fall off there. So something that's common in Houdini is if you want something to follow a curve like this, you can define these directions at these intervals by using a normal. And right now, I don't have any normals on these points. One nice way to get a couple things for free is to use a polyframe, and I'll explain what we're getting for free here. Again, like I said, as soon as I put this down, it is going to calculate normals. That's what this thing does. It calculates normals based on these options. So now this isn't really doing what I want, and it doesn't matter because I'm not gonna use the normals that this creates directly. What I'm interested in is this tangent, which is, if this is your normal, your tangent would come up at a 90-degree angle to it, perpendicular to it. So I'm going to rename my tangent to normal. And already that's really, really close to, actually this is exactly what I need. By default, I think this is at 2 edge. And you can see that's also pretty close to what we need. It's approximating that, but what I want is, it's like this normal, as it comes around the curve, I want it to point directly at its neighbor. And you just set that to first edge, and that's what you get. So we've established, just with this one node, we've established our normal from our tangent. Let me just label this normal from tangent. And that's good, but that's not our velocity. That's just a normal. So we need to convert this normal to a velocity. And if you look close, these normals are pointing. They're actually pointing from the top down, and we need to point these from the bottom up because we want our particles to flow from the bottom up. So the easiest way for me to do this is just with a wrangle. It's just one line of x. It's not hard. And I'm going to call this velocity from normal. And this is really simple vex. You can do this in a VOP if you're more familiar with that, but I find if I know exactly what I'm after, doing it in vex is a little bit quicker. So I'm just going to type the at symbol for defining an attribute, and this is going to be at v, which is our velocity, equals. You would think that it would just be the at our normal, at n, but we actually want this to be the inverse of that, so we just put a negative in front because we want our velocity, as I said, to travel the opposite way that these normals are facing. So now I should be able to see, and it's not showing me these trails, but we can visualize this easily by clicking on that information and then also clicking on this little v attribute. So now we can see that by clicking on this, it makes a visualizer. Let's actually edit this. We just don't want it to be quite so long. Okay, so now our velocity is pointing at each of these points. I think that's good, but let me actually double check this just to make sure that I'm still getting, actually using that 2 edge, even though the normals seemed, with first edge the normals were pointing right at one another, but I think because those are going the opposite way, what we see is this is, you know, if your particle's coming up here, it's going to travel right off this way. It's not going to get that second point. But I think if we use 2 edge, that actually calculates that a little bit closer, and maybe as we resample this a little bit more, we'll get something that's even closer to what we're after. All right, so that's half of it. That is the half that will give us, that defines directionality. Now I also want something that is going to define, I guess force. It may not actually be the proper way to talk about it, but that's how I'm going to say it. I want, the longer my curves are, I want the particles to go harder, you know, to move faster. So the way that I found to do that is pretty simple, is just using a measure stop. And this measure stop operates on primitives, you'll see. Let me turn off my points here. So this is going to operate on primitives, and we can calculate all kinds of different measurements from that. Now the way to find the length of a primitive is with the perimeter. So what that's going to do is export an attribute name called perimeter. I'll show you that in the spreadsheet. Again, this is a primitive attribute, so perimeter equals 1, and we got that because our length equals 1. Now if we go up higher than that, 2.8, let's see, 2.88. So basically all we're doing is we're getting this length attribute. But again, I actually don't want to call this perimeter. I do want to call it length, just because it's makes more sense to me. And now what we want to do is we want to use that length as a multiplier for our velocity, which is easy enough. But as we just talked about, this is not a point attribute. Our velocity is a point attribute, and right now our length is a primitive attribute. So we just need to promote that attribute promote, and we're going to change this from, let me grab my length attribute, just type that in, and our original class is primitive and our new class is point. And as soon as we did that, you can see we have our length here. Okay, so now that we've got our length, all we need to do is hop back into our wrangle that we created and add a multiply by the length. Okay, and this is the attribute length, not the vex function length, because we're using the at sign. So now we have our velocity that is being multiplied by the length. Now if we, let me see, and you can see, let me just pin this and you'll see it. So right now our velocity is going in y, and that's because, you know, we don't have, there's really not any variation in a direction, but just for the sake of showing this, I'll do this. So this is equals 1 right now because the length is 1 and also that direction is 1. But as I change this length, now our velocity is also changing. Okay, and just I guess one other way just to drive this home is I'll make a second copy, and I'll make one super tall, and also move it over, and then I'm just gonna merge these two together and pump that in there. Okay, so now I have two primitives, and one has velocity of 1, and you'll see the other is 2.5, which is the taller one. Yeah, 2.5. Okay, so now this is good. This is, I'm gonna enable this. The reason I'm doing this is I'm gonna pull this into our sim in just a second. I just want to have something to show. So I don't want that to be too far off. There we go. All right, so this is good. This is our velocity from our curves. I'm going to go ahead and save my file just in case anything bad happens. but this isn't what this is not what our dop sim or flip sim is going to expect. What it expects is velocity. I'm sorry. What it expects is a velocity volume, or at least in how we're going to use it, as it expects a velocity volume. So we need to create a VDB from, let's see, from these particles, because we're just going to do this at the point level. So VDB from particles, plug that in, and here's what we get. You can see this is way too big. I set this way down, and then this is just scale. This is just our point scale, more or less. Okay, so that's probably good for this demo purpose. And this isn't all. So what this has done, this has just given us a distance VDB that's called surface, and you can see that. There we go. So that's just given us one volume primitive called surface, and what we need is our velocity. So if we add, we can add volumes or add primitive volumes to this from our point attributes. We add velocity. Look, now we've got one called v, and we can rename this to vel, which is what that's going to be what DOPS sort of expects, and this is also going to be a displacement velocity. Okay, so this defines the vector type of the volume, and it is a velocity volume. Okay, so now I'm going to drop down a null and say out velocity, but I do want to visualize this just so it doesn't look like this still just looks like two curves. One thing we can do is use a volume slice. Okay, the volume slice, and that will give us, let me change the plane. Let me go to, this will just show us a 2D representation of our volume, which is useful to make sure that it's working, but we kind of already knew it was working. What this will do is it also shows you the density of your VDB grid. Maybe we want to go a little bit smaller than that. Yeah. And the other really useful thing is I'm just going to drop down a grid, and I want to show you volume. I want to show you the paths that these are going to take. So there's another SOP called volume trail, and what this does is it will take a velocity volume, and it will, I'm going to scatter some points on this grid. I'm actually going to make this grid a lot smaller as well. And I don't, yeah. So it'll take points, and it will create paths that the points are going to travel based on a velocity volume. And that's exactly what we're going to need. And this may not feel too useful when you've got such a simple shape as these couple of curves, but as we build this up, as we build a whole field of these curves, this is going to be pretty useful to see, and just to troubleshoot to make sure that's working. All right, so now we're going to hop into, we're going to bring this velocity volume into DOPS and push our sim around with it. For the sake of time, I already have the bulk of this simulation set up. This is what I created from the render that we saw at the head of the video. I've made a duplicate of it, and I've just deleted a few things that we're going to rebuild here. All these nodes are pretty much stock. They're default. There's nothing custom here yet. I have changed some parameters, and I'll walk through those after we make sure that we're getting the velocity volume working. Now, to bring that velocity in, we need a volume source, and by default, this is set to initialize the smoke. We're not doing that. We are bringing in velocity, and we do that by selecting the pump option. Our input is a SOP, so we just need to point to our velocity output, which is in velocity fields, out velocity, and we don't really need to pay attention to this scalar attribute. We're not dealing with the density. We are bringing in a vector attribute, velocity. So in SOPs, and when we created that out of the curves, the VDB we created, we changed the name of that VDB primitive to vel. So we need to specify that here. So source volume is vel, and the target field in DOPS is also vel. And the operation that we're doing, we're saying, hey, whatever the velocity is in this sim, add the velocity from this source to it. Lastly, a lot of times when we're sourcing in particles for our flip sims, we plug those into our sourcing tab. Now, don't get fooled by this. If you plug it in there, that's not going to work. Well, we're actually not sourcing particles into the sim. We're sourcing velocity into the sim, and that comes into the volume velocity input. Now you can put a merge and merge both of these in there. I just put this in line. It doesn't really matter. And let's quickly hit. Actually, I want to scale this up. I'm going to scale this to about 5, and let's see if our particles move along those curves that we had. Oh, and sure enough, look at that. One thing I want to do is I want to visualize my particles speed, not value, but speed. And there we go. So that is working as we expected. And you can even see that. So there's my shorter curve. I don't remember if that one is the curvy one or not. Let me just take a look. Yep. So my shorter curve is the one that's, let's see, I need to highlight that. Pop out. And there we go. So you can see how these particles start to approach that curve, but they don't really follow the curve so much because they're getting forced this way. And then actually our surface tension and our viscosity are just sucking those up in there. Sorry for the banging outside. My neighbors are working on something. So let's hop back into our .NET and we'll explain some of these, explain some of the settings that I have. Oops. Why is this getting an error? This is saying that we need a field that's not present. That's just because, yeah, that first one, there was no field called pump, right? And that's because we didn't define that. We're just worried about velocity. And so we just deleted that, and that's still working just fine. Now, a couple things. This is looking cool. This is exactly what we're telling it to do, but as this is set up right now, this is just going to continue to push particles throughout the entirety of the sim because the activation of our velocity is set to 1, which is always. And that is not what we want. What we want to do is we want this to emit for a few frames and then to stop. So I'm going to do that. You can keyframe that from 1 to 0 if you'd like. I'm just going to set this to say that the simulation frame $SF, when that is less than 5, be on, and when it's over 5, be off. So when this expression evaluates to true, that's going to equal 1, and when it evaluates to false, it's going to be 0. So now this is going to sort of add velocity for 5 frames, and then now it's going to turn off, and these are going to fall back down. They're going to fall down when their energy is run out, at least. That's really going. Let's see, let me actually, I'll turn this down even less, just to 2. And these are just values that you can play with the values to get the look that you want. But we can confirm that this is definitely working. We have 2 curves and our particles are going the direction of the curve, and the longer the curve, the harder the particles are pushing. So we've set it up and it's working well. And we're not going to stop there. We're gonna sort of, rather than just have a couple curves, we're going to have a field of curves that are going to define our splash effect here shortly. I just want to confirm that this is working. I'm going to talk through these some of these DOP nodes. So yeah, this is exactly what we're looking for. We have again, not to beat a dead horse, we've got this following up the direction of our curve. We're getting these cool droplets that are forming the further we get into our sim. And it's looking a little bit viscous, which is kind of a paint look that I'm going after. I'll talk through briefly what's going on in the sim. My flip object is, if you've seen some of my other tutorials, I generally will continuously emit particles into the sim, and that's not what I'm doing this time. Right now I'm just saying, hey, go whatever's plugged into the first the first input of this DOP.NET, which is these particles here, just use those as the fluid. And so that's set by particle field, and then you can either point to the SOP, or you can just use this op input path expression, and that's going to take those incoming particles, convert those into flip fluid, and then do the simulation. Inside the flip solver, a few things that I have changed. I like to always add an ID attribute. I've slowed this down a little bit. Rather than this timescale defaults to 1, which is real time, I've chosen to slow that down some by just cutting that in half. In the particle motion tab, I am using reseeding. It'll become more evident why I'm doing this when we add more velocity in here. It's just going to add. It's going to force a lot of particles into some of the thinner areas, and this default value is 1.5. That's one easy way to cram a lot of detail in there at the expense of it not being physically accurate anymore, is to really overcrank this surface sampling. I had it set to 20, so we'll leave it there. And then in the reseeding tab, I also am telling it to interpolate a couple of other attributes: ID, color, viscosity, and also this attribute ramp that I created that I'm really not going to go into in this tutorial, but I'm using this for shading. And if you're interested in how I use that, you can I use this to achieve that that gradation that's going on across the render that I had. I don't have that render up. So I use that ramp attribute to control these colors and with a redshift ramp at render time. So I'll explain that and comment that out and put that in the file that I upload to Gumroad. So that's why that's in the reseed tab. Really not much else has changed within the particle motion. Volume motion, I've enabled viscosity by attribute. I set that attribute, again, because this is a particle field, I set that viscosity attribute with a pop wrangle. I set that here, but I plug it into the particle velocity tab. So I set that to 10, just at viscosity equals 10. And then I have a pop drag to kind of add a little bit of air resistance to these as they're going up. And then the surface tension. And this, you can set your surface tension within the solver. I tend to do it with a micro solver. You can just type surface tension, and that brings that up. The default value is 0.1. I've cranked that to 1, I believe, to try to force these droplets together a little bit faster than they would form at the default value. And for the solver, that's really all I've changed. I've just added this surface tension, added some viscosity, and that's really it. So let's hop back over now, and I'll build a little bit more complicated velocity field. And I'm not, again, just for the sake of time, I am going to talk through this, not build it fresh. Again, I'll have a better version of this in my project file that I put on Gumroad. I plan on having a way to paint on a surface. So if you want, like, this is great. So this is driven by noise, just in this VOP. I've separated the different dimensions of our position and the XYZ values, and I'm adding noise to the Y value, and so you get this. But what happens if you say, I actually want this section over here to be a lot higher, and if you don't want to play with the noise settings, I'll add in a node where you can just paint a white value on here, and it'll make those go up. You can also add deformers to this. You can twist these around if you want. You can grab the same way that we did with these curves over here. You can make selections and scale those up, twist them around, whatever you want to do. These are just primitives, and you can deform them however you would like. And when you pump them through here, as you'll see, you get your velocity field the same way that we did with the curves. Now what I might need to do is make those points a little bit larger and I probably need to, I'm going to add one final resample before it goes into its the calculation for the velocity. I want to just visualize my points, and let's just get double the amount of points there, so that when we create our velocity volume here, that's just, those are going to be a little bit closer together. I still think that particle scale may be a bit too big. In essence, I just don't want a lot of gaps in here, and I don't want this to be too coarse. Maybe I'll change that to 3, and that's a little bit better. Oops, wrong way. All right, that should work for us. And let's hop back into our .NET and see what this is going to give us. Now I may pause, depending on how fast this goes, I may pause just so I'm not wasting a bunch of time. All right, so I went ahead and cached out this sim and just playing this back, and it's looking really good. So I'll hop back into the .NET and show you just the last little thing that I changed. So I have it cached out, and this is trying to resim everything, and I don't really need that, so I'm just going to hit escape here, and I'll show you. So the only thing I changed was this surface oversampling on the reseeding tab. I had that cranked up to 20. I pulled it back down a little bit, and I really don't think I changed anything else. Actually, I upped the surface tension just a bit, and that's really it. This is the result we get. Let me turn simulation off. And I'm really happy with it. I think it's, it's approaching what I'd want it to do. I'm really interested in these little sections that stay that sort of stay together and then get pulled in. I think that's really nice. And again, like I said, I'm not going to go over too much of the my meshing and render setup. If you're interested in that, you can always grab the file off Gumroad. But I do want to show you real quick why I've got this gradient happening. That gradient is generated by this. It's by this color, but what's going on underneath the color? This is a color value, but it's being generated by this ramp attribute. And the reason I want to do that is in Redshift, I want to use a Redshift ramp to generate these kinds of colors. And again, I push this through the sim so that gets carried out through the sim. It's not just static, and it's also that's being interpreted by the reseed. And the reason I do this in Redshift is when you try to start messing with these color attributes at a SOP level, Redshift really tends to bog down. I've gotten a few crashes from it, but when you do it at your shader level, and I said I wasn't going to get into it, but I can show you real fast. When you do this at your shader level, these are the final colors from my render. It doesn't bog down at all, and it happens. The updates are really, really fast, and I just tend to like that better. And I'll go ahead and do a quick render of this just to show you what the final render looks like. Let me make sure that I've got only that activated. This is my cached sim from the render that's on Vimeo and YouTube. This is what we built today. Really, really similar. It's almost the exact same setup. Let me come down here to my meshing and flag my material. This is my Redshift material. Let me flag that for rendering, then hop back over to my out context and open this in a render view. Let's see what we've got. It's looking really nice. Let me go up a few more frames so we get something that's fuller frame to render. And we're getting these nice droplets that are forming. They're breaking off in a really nice way. One more frame. And you can see how quick this renders. My machine's decent. It's Got two 1080 Ti's, and it's really cranking through this. I think probably my camera isn't positioned so great. Let me lock my camera and come on in a little bit. And there you have it. I've got some subsurface scattering going on to give this liquid a little bit nicer look. And again, that's pretty much it. So you've got a system to define these curves. Let me pull that up. We've got this velocity field that is defining our curves. Let me hop back in just to this. Oh, I'm sorry. We have a bunch of curves that are defining our velocity of the sim. So this sort of hilly pattern is giving us. You can see where this fluid is just following that pretty closely, especially initially, and then when we stop sourcing that velocity into the scene, that's when the surface tension really takes over. And that's basically it. So I hope you enjoyed this. I hope you found it useful. Again, if you want to grab this file with, I'll extend the functionality of this a little bit before I post it to Gumroad, so you can paint some areas of influence to have greater influence. You can also, as I talked about, you can merge all this together and have individual curves. You can place those where you want. I think that's my larger curve. So you can place these curves wherever you want and just pipe this directly into here. And any curve that you put into this system is going to affect your velocity. So I think this is a great way of art directing some sims, because inevitably, if you're doing this for a client or even for yourself, you get something going that's maybe halfway there, even better than halfway there, but you're like, you know what, this would be perfect if it just shot up really hard over here. And so now you can do that. Or if you don't want to merge these in and you just want to make selections, like, you absolutely can just grab this, do an edit, change this from surface to radius, and you can pull up hills as much as you want, or if you say that, you know what, this is working, but this one's too high, let's move that down. Or, you know what, I want to add some twist to it. You can, and all this will carry through your sim. So again, I hope you see the value in taking the time to build this out rather than just throw some stock forces in there. And I hope you also see the value in just using the tools that are available in the standard tools that are available in Houdini to get some really nice looking some splashes. All right, so that's it. So thanks again for watching. If you found this useful, or if you want more information, check me out at whatifound.net. You'll find all the social links there. You can follow me on YouTube, Vimeo, Twitter, wherever you like. Hope you enjoyed it. Thanks so much for watching. All right, so I wanted to hop right back in and just say, after recording this, after playing with my setup for a little bit longer, I kept thinking, wouldn't it be nice if I was able to retime this and I wouldn't have to rely on reseeding to get some of those some of the details and to get some of that thin sheeting? Wouldn't it be nice to not have to reseed? Is there a better way to do that? So after spending a day or so poking around online, digging through forums, I found some really helpful advice from some Houdini users who are a lot further along than I am. I just wanted to share the results really quickly. So what we can see here is I have a lot fewer particles. I am able to retime this. I didn't sim this fast. This is using the game dev toolset retime that retimes your animation via this nice ramp. Here's the sim, and what this is using is it's using some custom surface tension and a custom hole filling setup. Now, I didn't come up with either of these tools. I did modify them to work in conjunction with one another in a way that really worked for my setup, that let me keep some of these nice details up here and have that drop break off. The whole filling by default never let anything break up. So what I'm going to do is I'm going to record another video in the next week or so about how to extend the setup that you just saw, with some help from users on forums who are posting tools that they're creating. And just basically I'm just going to do a walkthrough, either a video or a write-up, on how to find help when you need it, and how to apply that in a smart way that works for your own setup and that'll give you some more flexibility. So all that to say, and I'll show you the render that I created with my new setup. All that to say, you get happy with something, don't stop there. There's always ways to push your ideas further, and there's so many helpful people online to learn from. So in my next video, that's what we're going to talk through, is how to extend the setup that we have. I'm using the same velocity system that we built, but how to extend it with the help of resources that you find online. All right, thanks again.